Welcome again to this next example in work energy power, and we are basically dealing with work energy theorem. The question or the example reads, the stopping distance of a vehicle is an important safety factor. Assuming a constant braking force, use work energy theorem to show that a vehicle's stopping distance is proportional to the square of its initial speed. If the automobile, this is the next part of the question, if the automobile traveling at 45 km per hour is brought to a stop in 50 meters, what would be the stopping distance for an initial speed of 90 km per hour? So let's see that the question, interpret the question. They are saying the vehicle's stopping speed, stopping distance is very important. For example, when you're running a car and then you apply brakes, it does not stop immediately because of the its momentum, initial momentum or inertia. It keeps on going as you apply brakes, and then after a certain distance it comes to rest. So that distance from the time you apply brakes to where it stops is the stopping distance. Now let's see how it is related to the initial speed. The other thing we need to know is that since it is a stopping distance, it means that the final velocity is zero. So we recall the work energy theorem, which says that the work done by a force is equal to the change in kinetic energy. So the work done is going to be a half m v final squared minus a half m v initial squared. Now in this case, because the final velocity is zero, that one goes out of the equation, and we remain with work done equal to work done by a force, which is actually force times distance, going to be a half, which is negative m v initial squared. And again, back to the question, they're saying that important factor, assuming a constant braking force. So that means the braking force in this equation, which is F, is going to be constant. We want to prove that the distance d is proportional to the initial velocity squared. Therefore we make d the subject. Now d is going to be equal to negative 1 over 2d times m, the whole of this in bracket, times v initial squared. So whatever we have in the bracket is a constant. We can conclude that d is proportional to v initial squared. So we have proved that. Now the next part of the question says that if an automobile is traveling at 45 kilometers per hour, now is brought to rest in 50 meters. So we know that when the speed is 45, we can use proportions, because now we have seen that how they are related. We have seen that d is proportional to the square of the initial speed. Therefore we would say for 50 meters this will correspond for a car which is moving at 45 kilometers per hour, it will be stopped in 50 meters. Therefore we would say that is corresponding to this squared. Then what will be the distance? Maybe x. If now the car is moving at 90 km per hour. So if that's true, that is squared. This is how they are related. If we cross multiply, we shall come up with x equal to 50 multiplied by 90 km per hour. We can maintain the units, squared divided by 45 km per hour squared. The units on the right are going to cancel out. Hope you can clearly see that up here we shall have kilometers squared per hour squared, even down, so they will cancel out, and then we remain with x equal to 50 times 90 squared, 50 times 90 squared divided by 45, which is also squared, and this will directly give us 200 meters. Which means that for a car which is initially moving at 90 kilometers per hour, When brakes are applied, it will stop after traveling 200 meters. Okay, so now this is your exercise. I can read it for you. A 2.5 gram bullet traveling at 350 meters per second hits a tree and slows uniformly to stop while penetrating a distance of 12 centimeters into a tree's trunk. What force was exerted on the bullet in bringing it to rest? In your brackets here, you have that as the answer. Try it out and see the answer. Make sure you share your ideas and share your views to me.